Welcome to a lesson with Dr. Powell. Let's talk about how quaternions are related to the cross and the dot product. First, let's think about what quaternions are made of. They're made of a real part and an imaginary part. What if we take a vector that just is imaginary? It's going to be orthogonal to the real axis, which you don't really see because it's a coordinate which the first coordinate is not the one we see, even though it's real. We just see the imaginary part, the last three coordinates. So what if we just take a vector that comes from the last three coordinates? Let's call it u. And let's think of u as being a quaternion. Example, u could be something like I minus j plus 2k, completely imaginary. Now, what if we look at negative u, faces opposite, and in quaternion language, we could write this as u overline bar, the conjugate of u. And now why would we do that? Well, think about complex numbers. If we have 2 plus I, its conjugate is 2 minus I. What did we do? We made the imaginary part negative. Okay, now, what if we just had I? What's its conjugate? Well, just its negative. Make the imaginary part negative. Hence, negative means the same thing as conjugate. So we're going to use the notation u bar to represent negative u. Okay. Now, what if we multiply by u bar? What happens? Now, just as for complex, when we multiply by something, we can make a new set of axes with regards to that particular complex number, and then plot the second guy in it, and that's how we multiply. Same thing works here. U bar will be like the new real axis facing down here if we multiply by it. What is that going to do? If we plot u with respect to it, actually u is going to be right here. It's going to be real. It rotates it right down to be real, just as it would for imaginaries. So if we multiply by u bar, the effect is u bar will be now real. Now, not only will it be rotated, but it'll also be expanded by the size of u bar, which is the same as the size of u, the length of this. So that's great. So what we get is u times u bar is now on the real line. Okay, what's the utility of that? Well, what if we take two vectors, v and u? Okay. Now, thinking about this for a second, we can kind of think of there being an orthogonal component for v and a projection of v onto u. Now, what if we want to study that idea? The best way to study that, just as for complex numbers, is to multiply both of these guys by something to rotate this guy to the real line, so that this part is nothing but the imaginary component of the multiplication of v after we multiply, and this would now turn into the real part, and we can just read off the projection and the imaginary part just right away when we rotate it down. So what we're going to do is we're going to think of u and v as being quaternions. So we can do some multiplication. And if we multiply by conjugate u bar, what we end up getting is we get the same picture rotated and expanded. And if we take the imaginary part of this guy right here, that'll be exactly that vector right there. Of course, this will be real. We won't see the real part, but we actually will see this. This is purely imaginary with no real component. So we'll actually see this in 3 space. So what we end up getting is the imaginary part of v u bar is equal to that, and we give this a name. We call it u cross v. So it's an imaginary part of a multiplication here of quaternions. The real part in this multiplication, v u bar, is actually equal to something we call the dot product, which we've seen before. And these ideas all coincide just perfectly. Okay. Now, when we're looking at this, let's think for a minute about what's happening. You see v u bar. When we multiply that together, and we're thinking of v and u as being imaginary things, if we multiply something imaginary something else to something else, it makes the result orthogonal to what we started with here. But since they're both imaginary, the product will be orthogonal to both of them, at least in quaternion land. So we're going to get a result which is has four different entries in it, whatever they are. There might be a real part in this multiplication. But if we compare it to u and v, which have a 0 in that component, and we do a dot product, notice we get 0 here. So really, orthogonality has to happen here. The dot product here has to be 0. So really, if we project again for the real part, project again onto the imaginary part, we get this thing right here actually has to be orthogonal to be what both u and v were to begin with, which is kind of a neat idea. And we'll talk about that right now. Okay, so what we end up getting is if we think of the plane where u and v reside, u is facing this way, and v is facing that way. Okay, maybe we have a counterclockwise rotation right to there. So we're going to try to visualize where u cross v is going to be located. It has to be orthogonal to both of these, and there's only one line coming up from this plane back and forth, which represents directions that are orthogonal. So it's either going to be up or down. Only two options for u for what u cross v is. Only two options. And so u cross v is going to be up this direction or that direction. Which direction? Let's take a look at another example with I and j. Now, in the definition of quaternions, we take I and we visualize I and j right here, counterclockwise from each other in a visualization. And we also visualize k counterclockwise here from there. Now, thinking about this idea and thinking of this plane as being where I and j live, in quaternions, we define k to be the product I times j, which is k, which is purely imaginary, which means cross products are the same. So I cross j is actually equal to k. Now, if you were to rotate or multiply all these things by something, this same picture would be rotated as well, very nicely. So in fact, we could even rotate a picture here, so u would be in line with I. Now think about something else. When we take imaginary and real parts, if we're only concerned with the imaginary part, thinking about this, we want maybe just this component of the vector v, and not this component that actually has projection. But really, this is the only part that really counts. So the cross product is the same as if we took this part and that part, which is like taking, if we rotate it to this picture, I and j. And so I times j was visualized with going upward from here, counterclockwise. So similarly, if u is in place of I, we can actually just visualize the ijk thing every single time to get the direction of the cross product. So if u, and then we have this component right here, cross together will give you something. If you rotate this, you can imagine the u following where the I is, this component following where the j is, and k will actually be going straight up here, or u cross v will be up. Now, if we were to think the opposite way, what if we did v cross u in the same picture? V would flip to where the I is. But in order to do that effectively, you kind of have to turn this picture upside down. So V will land on the I, and then the U and its component would land on the J place. But in that case, when it's turned upside down, this picture would be turned upside down as well, and K would be down. So in other words, would be facing down here. So V cross U would be going down that way. If you think about that just one more time, let's think. So if we had V first going the opposite direction, so flip flop. So yeah, that would come down around and be upside down. Okay, so that's kind of a way of picturing which direction U cross V is going to go. So U cross V is going to be orthogonal to both of the original vectors. Now, U cross V is also that length in the if I have my two vectors and I did my rotation. So U and V, or however I'm doing it. It's also this distance in the parallelogram that I get after I've kind of expanded both of these by the length of U. And it's now sitting on the real line, which means this is actually equal to the length of U times the height of the triangle, which is actually the area of the parallelogram formed between those in space. So we kind of rotate this down and we can actually see that right away. This imaginary part, if you take the length of it, will actually be the area of that parallelogram. Kind of neat. Now, if U is actually a unit vector, this part's just 1. So the real part will actually be the projection, which is what we'd expect for a dot product. So that's a little description of how quaternion multiplication relates to the cross product and the dot product. But one more note before we finish, and that is, notice that when things are imaginary, interchanging the order does nothing but make it the negative of what it started with. Notice how we're doing something like we're putting a U bar last, and then we're putting V to describe what U cross V is. That looks a little out of order. What if we interchange these orders to make it negative? We'd get negative U bar V, and now this is just U. Of course, that interchange of order only really works for imaginary products and imaginary results. For I squared and J squared and stuff, doesn't quite work. So really, the real part's going to be affected and messed up if we did this. That's why we do this. However, the imaginary part is not. The imaginary part of this is actually the same as the imaginary part of this. So if you want, you can actually, for ease, just do UV as quaternions multiplied together, take the imaginary part, and that's going to be equal to the cross product. However, the real part will not be the dot product, and now it'd have to be the real part of that. But it will be the negative of the dot product, negative U dot V. Thanks for watching.